Here we go. Lesson 2.2. This is about different types of thinking, specifically inductive and deductive thinking. Here's some of the words you're going to use during the lesson: conjecture, counterexample, deductive reasoning, inductive reasoning, and hypothesis and conclusion. Hopefully those last two you've seen before in your science classes, and it's pretty similar to what we're using in here. All right, straight off, here's a little mental image. This first picture here is an example of what we would label as inductive reasoning. And it's a nice little GIF, so to speak, a little picture that helps us think about what is inductive reasoning. So if you have a situation where you are given a lot of different cases, yes? Say you got your best friend and one day he comes over to your house late, and the next day he comes late again, and then the following day he comes late. 2 weeks later, he arrives again 5 minutes after you asked him to come. Finally, he shows up yet again on the 5th time late. So you would say, this friend of mine is always going to show up tardy. I'm just going to have to live with the fact that my friend is not going to arrive on time. All right? And that would be inductive reasoning. So we have a bunch of different cases, and then we form a rule about that. It's kind of a harsh rule about your friend. Hopefully you're not so judgmental as that example was. The second one is a rule, and this is the case of what we would say would be deductive reasoning. And we don't start with the examples, but we start with what would be the rule. And the rule would be like, okay, when you leave the house, you have to call me whenever you get to your destination. And so on Thursday, when you go out to the Dairy Queen with your friend, you call back at home and said, Mom, I got there, I'm safe. Or the following weekend, you go out on Sunday to the movies, and again, text, call Mom, made it, safe, and so on and so forth. So whenever you go out, yes, you make that call. And that would be, there is the rule, okay? Here's the rule. And then we apply that rule to all those instances. And again, deductive reasoning is just the opposite. We have all the little examples, and then from that we say, oh, yeah, I see what's going on here. So those were kind of like familiar examples. Let's move to an area of mathematics and use those examples. So let's say I have a little diagram, and I say, how many new matchsticks do you need to keep the pattern going? Now, I'm going to draw the next pattern. So there we have another little square. And again, I go again, yes, and so on and so forth. And you can visually see that the rule would be, from inductiveness, from looking at the examples, that every time I am drawing 3 new little matchsticks to create a new box. Okay, and so the rule would be you need 3 matchsticks every time. Okay, whatever you start off with, in this case here we started with 4, then we would always need 3. This, again, is an example of inductive reasoning. All right, second example of inductive reasoning. What are the next numbers in the sequence? This one's a little bit tricky, because if you look at the numbers, you could be thinking a lot of different things about what that next number is, and hopefully right now you're kind of like trying to guess, what is that going to be? Hopefully you've written down some cases, all right? And maybe you looked at like what's going on from 2 to 3 and then from 3 to 5. Well, then a lot of people would say, okay, I see the pattern. I'm going up by 1, I'm going up by 2, so the next one would be 8. and then the next one would be 12. And that's one way to look at this numbers. And this would be that every time you add an extra value, an extra number. Okay? All right. You forgot the word add there. All right? Now, another way, you could say, no, I have a counterexample to that rule. I'm not thinking of 8 and 12. I'm actually thinking of some other numbers. And you could say, well, the next number in my sequence was 7, and then it was 11. And you may say, well, how is that a counterexample? Well, there's different numbers, right? So from that example, we came up with a different rule, and that would be the next prime number. Now again, there could be a third person out there who's thinking of something else. And they say, I even have a better counterexample, like 2 other numbers that could fill that sequence that would not be either of these. And again, counterexample is finding an example that goes against the rule. So another case would be, I don't know if you've heard of Fibonacci sequence, but a Fibonacci sequence says you just add the previous 2 numbers. So 2 plus 3 is 5, and 3 plus 5 is 8, and 5 plus 8 is 13. All right? And so here we would come up with yet another case of, this would be the Fibonacci sequence. All right, counterexamples, very important. They kind of break the rule. All right, and in this case here, again, we were using inductive reasoning to find the, what would be the rule, right? We're looking at the different patterns that show up, but, and then we found rules that break it, or examples that break it. Well, then what is deductive reasoning? So here's a case of deductive reasoning. If I said if x equals 6, then you would say, oh, yeah, I know what x squared is. Not 12, but 36, right? All right. A couple things here. How did you know that? Well, first of all, we knew the hypothesis. What is the hypothesis in this case? It's that. Yeah? What's the conclusion of this statement? The conclusion is then x squared is 36. Right? And we have a rule in the back of our brain that says if I give you a value and I give you an x squared, then we know what's going to happen, right? Because somebody taught you at some point that x squared means you multiply the number by itself. So that's using a deductive reasoning, that from the rule, we arrive at a specific case, a specific example of the rule. All right? So again, the hypothesis always follows the, I should use different colors here. So how about we do this? So the conclusion follows the then, and the hypothesis follows the if. All right. Let me now have you think about something coming up here in October. End of October, we have something called Halloween. And there's a rule that most people follow about trick-or-treaters, that if a child visits you on the 31st in the evening, then you're nice, you give them candy. Okay, notice how we have here, much like in the last example, we have a hypothesis and we have a conclusion, right? It's kind of a deductive reasoning. Now, say a kid shows up, your next door neighbor, and I'll call them Jake. All right, my neighbor's Jake. And if Jake shows up at my house, it's hard to call him a kid anymore because he's probably in his mid to late 20s, but So I don't know that he qualifies as a child, but if he did and rang my doorbell and said trick or treat, then I would give him candy. He would get candy from me. I would hand it out. And this is called the law of detachment. And the law of detachment says, if you have a rule, like this rule, and then I have a specific case, like Jake, or, Elizabeth. His sister Elizabeth shows up, right? Again, probably a little bit old for showing up at my door, but I'm nice. I give her candy. Okay? So anytime we have an example of that rule, right, then we would apply that situation. So the law of detachment says, given a rule, rule plus a case gives us the result. Or an example, rule plus example. Now, let's say we had another rule show up. Last one example here, a rule about candy. If you get candy, then you, I don't know how you would fill that in. I would say something like, then you, we'll just say we're happy. Yeah, we're pleased that we got something to munch on. All right? So, now I can take these two examples and put them together. The rule about trick-or-treaters and the rule about candy. How so, you say? Well, if a child visits on the 31st, then they get candy. If they get candy, then we're happy. So the law of syllogism would say, an example for this case would be, if a child visits your door, then he or she is happy. Okay? So the rule of syllogism basically says if you have two conditions, so A, then B, right? So you know that this is your hypothesis, this is your conclusion, and then if you start with the hypothesis of the last thing, right, as a hypothesis, and then I tack on another C condition, right, I don't know what that might be, then I can skip and go straight from here to here, okay? So the rule of syllogism says then A will give us C. All right? So quick summary, inductive, deductive thinking. This is kind of the idea, from the many to the one, or from the one to the many. We develop examples. We look at a lot of examples. We develop a rule. Yeah? And if you ever find something that breaks the rule, then you would call that a counterexample. We have the basic structure of most rules will fall into this category of a hypothesis and a conclusion. And so we have these examples, these rules, and then if we have a case of that rule, then we have the result of getting candy, right? Specific instances of the rule. And then we can put rules together. In this case here, if we put two of the conditions together, we can then shorten it up with a then C. The rule of syllogism, sometimes called the chain rule. Hope that explains the lesson. Good luck as you go through and do lesson 2-2.